This is part 3 in our series of lectures on section 1.6, and in this lecture I want to say a few words about universally quantified statements and existentially quantified statements. Now, if you're given an existentially quantified statement like this, and suppose you want to prove that it's true, and suppose you're giving a constructive proof of that, then you either explicitly have to produce an x and then verify that that particular x works. In other words, it makes p of x true. And so in your proof you would write something like choose x to be, and then you explain how you're choosing that x, and then you verify that that specific x works. Or another possibility is you already have a candidate x. It's already written down on the page. You're just sort of highlighting it, and it remains only to verify that p of x is true for that particular x. On the other hand, if you want to prove a universally quantified statement is true, it doesn't prove anything if you merely plug in a specific x and verify it's true. It might be a good idea to check it for a few x's just to convince yourself that you believe it's true, but that won't really prove anything. You have to, in order to really prove it, you have to give yourself a generic x, and you have to prove for that generic x that p of x is true. So let's illustrate that with two very simple exercises. This statement here, this part of it is the same for both, but in one we have existentially quantified the variable, and in the other we've universally quantified it. So go ahead and write a proof of this one here. There exists a real number x such that x squared plus x plus 1 is positive. Put your video on pause and write down the proof. It's just one line. So here's my proof. All I have to do is produce a single x, it doesn't matter which one, just as long as it makes that true. So I say choose x equal to 3, and then I just verify that this is true for that x. Then x squared plus x plus 1 turns out to be 13, which is positive, and so that's the end of the proof. Now try to prove this one. This is a little bit more difficult. You have to give yourself a generic x, and you have to prove that this always turns out to be positive. How could you do that? You know, it might be a good idea to check it for a few x's to see if it really works. It might even be a good idea to draw the graph of the function y equals x squared plus x plus 1 to convince yourself that it always lies above the x-axis. That would make you believe that this is true for all x, but none of those things would actually help you to get the proof. You'd need sort of a new idea to come up with the proof. And just as a hint, you remember the old trick of completing the square. So put your video on pause and see if you can come up with the proof. It may take a couple of lines to do it, but when you come back you can see my solution. Okay, here's my proof. We have to begin by saying let x be a real number. And now there's nothing left to do except just to prove that this happens. So what I do is I start working on this in order to convince myself that it's positive. So I say, then x squared plus x plus 1 is equal to this. And essentially what I'm doing is I'm completing the square. I'm taking half of this coefficient of 1 and I'm squaring it. And that gives me a quarter. And then in order to get it to add up to 1, I have to put in a 3/4. And now this part is a perfect square. It's x plus a half quantity squared plus 3/4. And now the point is, you see, this is non-negative because it's a square. And this is, you're adding 3/4 to that. So this thing has to be at least 3/4. Okay, so since x plus a half squared is greater or equal to 0, it follows that this is at least 3/4, hence positive. Now, it's not always the case that your intention is to prove that this is true. Sometimes you already know it's true and you just simply want to work with it. This, for example, happens or quite often when you're working with working definitions. So let me show you a new working definition. This is the working definition of rational number. A real number x is called rational, provided there exist integers m and n such that x is equal to m over n. So that's your working definition. The set of rational numbers is denoted by the letter q. You'll notice the extra little line on the q. Okay, so it's worthwhile writing it in symbols. I'm just writing the end of the definition in symbols. I've got a number x, and I want to write in symbols what it would mean for that particular x to be rational. It means there exist integers m and n such that x is equal to m over n. Now here's an exercise for you. I want you to prove that for all real numbers x and y, if x and y are rational, then x plus y over 2 is also rational. First of all, could you please put that in symbols for me? So put your video on pause and put that thing in symbols. Okay, in symbols it says for all real numbers x and y, if x and y are rational, then x plus y over 2 is rational. Now, how do you prove something like that? Well, you know how to begin, because that's universally quantified. You start by saying, let x and y be real, and then assume that you're going to be able to give a direct proof. Suppose x and y are rational. Well, now you see we get to use the working definition of rational, which is here. The fact that I know x is rational means that I know that this is true. That's what I meant when I said that at the beginning. I know that it's true, I just simply want to make use of it. So I have the right to say that there exist integers m and n such that x is equal to m and n. And I also have the right to say that since y is rational, there exist two other integers, I don't know, r and s, such that y is equal to r over s. Okay, then working with that, I somehow want to deduce that x plus y over 2 is rational. So I'll leave that for you to see if you can figure out. So go ahead and you write up the proof. Here you see I've written it all out again for you. Write up the proof of this. It's better to look at it in symbols. And put your video on pause, and when you come back you can look at my proof. So here's my proof. As usual, we start with let x and y be real numbers. Suppose x and y are rational. So now I'm going to use the working definition here of rational. Then there exist integers a, b, c, and d such that x is equal to a over b and y is equal to c over d. Sorry, I should have put exist instead of exists because it's plural. Anyway, now I wanted to do something about x plus y over 2, and so it's natural for me to just simply do this calculation, and I get this. Now, in order for me to deduce that this thing is rational, I don't have to go through any big contortions to do it. I don't need to introduce any new variable names. I just need to observe that this is an integer and this is an integer. Since both these are integers, it follows by definition that this quantity is rational because it's a ratio of integers. I don't need to introduce new names for those things. And that's the proof.